Welcome back to the class. In the last class, we were studying about the reactions of synthetic importance. We studied in that class one oxidation and one reduction reaction. The oxidation reaction was the Oppenheimer reaction or Oppenheimer oxidation reaction. The second one was the Finar reduction reaction. In today's class, we will study about three reduction reactions. The first one is Clemmenson reduction reaction. The second one is Birch reduction reaction. Third one is using two metal hydrides. So one is sodium borohydride. The second one is aluminum or lithium aluminum hydride. So first let's study about Clemmenson reduction reaction. So what is Clemmenson reduction reaction? So it is about reducing aldehydes and ketones to methylene group. So this is a methylene group. So methylene group is nothing but just your hydrocarbon. So that means it is going to convert the aldehyde or keto group to the methylene. So what is the reducing agent we are using here? That is zinc amalgam. Zinc amalgam is nothing but zinc and mercury combination. Right, along with the zinc and mercury, so we are going to take hydrochloric acid. That means we are using acidic condition here. One thing you have to observe here, this Clemmenson reduction reaction is very similar to Wolff-Kishner reaction that we studied in the last class. There also we were converting aldehyde and ketones to the hydrocarbons, but using the basic medium. We used hydrazine and potassium hydroxide. That was the basic condition. Here we are using zinc amalgam and hydrochloric acid. This is a acidic condition. This reaction is particularly effective in aryl alkyl ketones. We'll see that in next slide. So this is the general formula for the reaction. Here the keto group. Okay, you are converting that to hydrocarbon CH2 group. So this here the R1 can be alkyl. This can be alkyl, right? This can be alkyl or CH3 or C2H5, right? Alkyl. This can be alkyl group, or this can be aryl group. This can be aryl group like this with the vinyl ring, right? Even this can be alkyl group, same thing. This can be aryl group. R2 can be aryl group, or R2 can also be hydrogen. Right? When it is hydrogen, then it is an aldehyde. Okay, you are subjecting this ketone to with the zinc amalgam and hydrochloric acid, and you are going to get the hydrocarbon group over here. Alright, here is an example. Acetone CH3, okay, carbon double bond O, that is acetone, and you are doing Clemmenson reduction reaction here using zinc, mercury, and hydrochloric acid. So you are going to get N-propene. So this CO group is replaced by CH2, so that is going to be N-propane for that acetone. So let's look into the mechanism of this reaction, how the reaction is going to take place. It's very interesting how one group is going to get converted to another group using just the electrons and the bonding transfers. Alright, here is your ketone or aldehyde, if you replace this by H, so that is going to be your aldehyde. In exam, they can ask maybe show the mechanism of reaction of Clemmensen reduction in case of aldehydes, and then you'll have to replace this R by H. If they ask for ketone, only ketone, then you can retain that R over here. So this is your ketone. So you have electronegative oxygen over here in the keto group, right? It is going to, because it is electronegative, it is going to attract the pi bond electrons from here, right? So it is going to be partially negatively charged, and because the electrons are going towards that, so this is going to be partially positive charge. So now zinc as a catalyst, it will have, zinc is electron donor. It will have electrons, free electrons with it to give out. So it is going to attack on this partially positive carbon. So it is going to give the electrons, because it is giving the electrons, it is going to be negatively charged now, right? Because the electrons, it is negatively charged, and the electrons over here, they are going to complete over at this double bond, 5 electron, they are going to completely shift to the oxygen, because there is a repulsion between these electrons and this electron over here. Anyway, oxygen wants the electrons, and those electrons are going towards oxygen, and it's going to convert the partially negative oxygen to negative oxygen. So oxygen is going to get negatively charged. So you know this is acidic medium, and you have hydrochloric acid. From that hydrochloric acid, two out of two hydrogens, one hydrogen is going to attack on this negatively charged carbon. So it is going to get attached over there, right? One hydrogen over here and one more hydrogen. What it is going to do? It is going to attack on this negatively charged oxygen. There is negatively charged oxygen here, so it is going to attack there. So here is the hydrogen, it is over there, and it is going to form the alcoholic group over here. Now what will happen? Again, because of this negatively charged oxygen, these electrons are going to be more towards the oxygen, so it is going to be partially negative because of that. And this the hydrogen, however, it is there in the acidic medium, right? Because it is acidic medium, we have hydrogen in the medium because of hydrochloric acid. So that hydrogen, again, it is going to go attach with this oxygen. So it is going to form a bond over here. Now what will happen? Again, because of this oxygen, the electrons are going to be towards oxygen, and it is going to form water. So water is going to get eliminated here. So because this bond is used, the electrons from these bonds are used to remove that water, the carbon is going to get positively charged. The proton of carbon is going to get exposed, so it is positively charged now. Now you know the zinc has got electrons, it can give those electrons, right? It is an electron donor, so it is going to give those electrons to this carbon, and this carbon is going to get negatively charged now. And because this is negatively charged, there are protons in the reaction medium, right? Because of the acidic HCl, that is going to attack on this carbon, because it is negatively charged, and it's going to form the hydrogen bond over there. So we got the second hydrogen over here. So We got the hydrocarbon, the keto group converted to hydrocarbon. So this is the reaction mechanism involved. Right. Next, we will look into applications of Clemmensen reduction. The first one is it reduces the ketones formed in Friedel-Crafts acylation. This is the product of Friedel-Crafts acylation on the benzene. So you have benzene, you know the Friedel-Crafts acylation reaction. It is electrophilic substitution reaction. Suppose this is attacked by Cl, right? The acyl group has is the substitution over here on the benzene, right? Friedel-Crafts acylation is electrophilic substitution reaction product, right? So this one we are going to subject to Clemmensen reduction using zinc amalgam and hydrochloric acid. So you can remove this keto group from here and make it into a straight chain hydrocarbon. So that is the uh, use of this reaction. So you can convert the keto group in the chain to the hydrocarbons. So here you are converting acetophenol to ethyl benzene. Alright, next explication, the reaction is more effective in the reduction of a cyclic ketone. Suppose you have a cyclic ketone like this. This is a cyclic ketone. You can convert this using Clemmensen reduction to, or you can remove that cyclic keto group. So you can convert that to this product. So you can remove that cyclic ketones. So next is the limitations in this reaction. What are the drawbacks in the reactions? You cannot convert alpha beta keto acids with phenyl ring. You cannot reduce that. Right now, this is your carboxylic acid. This is alpha ketone because it is attached to the alpha carbon. This is alpha carbon, this is beta carbon to this carboxylic acid. So this is alpha keto acid, right, with the phenyl ring. So such keto acids or alpha keto acids cannot be converted. You cannot reduce them. Also beta keto acid. Beta keto acid with the phenyl ring, you cannot reduce that using the Clemmensen reduction reaction. So this is about the Clemmensen reduction reaction. Next we will go for Birch reduction reaction. So what is Birch reduction? Birch reduction is partial reduction. It is not complete reduction. It says it is a partial reduction of aromatic compounds. So it is partial reduction of aromatic compounds. Here the example benzene, right? You are reducing, but you are going to get the partial reduction product. We'll see that in a little bit. So what are you going to get? 1,4 reduction is going to take place. This is the aromatic compound 1, 2, 3, 4, right? Reduction is going to take place at position number 1 and position number 4. So it is only the partial reduction. You are not, these position number 2, 3, 5, 6 are not going to get reduced. So one for reduction to provide unconjugated cyclohexadiene. So this is conjugated diene. The conjugated means the double bonds one after another carbon. So those are conjugated dienes. Unconjugated means there is interruption in between. They are not like in sequence. So you're going to get unconjugated. This is unconjugated hexadiene. The reduction is conducted. What is the reaction? What is the reagent we are going to use here? It is conducted by sodium or lithium. You can take sodium or even lithium, sodium or lithium metal in liquid ammonia. and in the presence of alcohol. We have to take the liquid ammonia and the medium, the reaction medium, the solvent is alcohol. All right, let's look at the mechanism in this reaction. Let's see how the reaction is going to take place. This is the mechanism. Let's see. Now you have sodium, right? Sodium or lithium you are taking. The sodium, the atomic number is 11, right? 11 in that 2 electrons in the first principal orbital and 8 electrons in the second principal orbital, and it's going to have 1 electron in the outermost orbital. It is going to have 1 electron in the outermost orbital, and it's ready to give that outermost electron. So that's what is going to happen here with the sodium. We have put the dot here, the single electron. Um, so this sodium is going to give the electron to this carbon, to this carbon over here, right? Going to give the electron. And what is going to happen? All these will have the electrons, the pi bonds, right? Pi bonds will have the 2 electrons here, and in this between this carbon, between these 2 carbons, the one of the pi electron is also going to go to this carbon, right, the top carbon. So it is going to get 1 electron from sodium and 1 electron from the pi bond. So it is going to be negatively charged now. So this carbon is negatively charged. That's why it is called radical anion. It is not just free radical, it is a radical anion. So this is negatively charged, and we have alcohol in the medium, right? Alcohol, ROH, right? The hydrogen from this alcohol is going to attack here for this anion, for the negatively charged this anion, for the negatively charged carbon. So it is going to form that hydrogen over there, hydrogen bond, right? Now here what happens, because this electron from here has gone to here, this electron is going to move here, and it is going to form double bond over here. Subsequently this electron and this electron, where is the double bond is coming from? 1 electron from here and 1 electron from this bond. So this the another electron from this is going to shift to this carbon. So that is what the dot over here, the this is the electron from this pi bond. So now again it's a radical now. It's like a free radical now. It has got only 1 electron over here. Now the sodium with the 1 electron, 1 free electron, it is going to give its electron to this radical, right? It is going to give to this carbon. So you're going to get 2 electrons here, and again it is going to be radical anions. Again what will happen? The hydrogen from the alcohol going to go attached to this, carbon, and it is going to form another hydrogen over here. So that is how you get the hydrocarbon positions over here, or they get saturated over here. This is only the partial saturation. So this is the reaction mechanism of Birch reduction. So next is the application: heterocyclic compounds such as pyrols, furans, and Pyrimidines are also reduced. It is not just the benzene ring. So the heterocyclic compounds such as pyrols, furans, and pyrimidines, they are also going to get reduced, the partially reduced. Conjugated alkenes, alpha, beta, unsaturated carbonyl compounds, internal alkynes, and styrene derivatives are also getting reduced. So it is not just the aromatic compound, even conjugated alkenes are going to get reduced. So So this is conjugated alkene, straight chain alkene. So they you can reduce this, partially reduce this. Even alpha beta unsaturated carbonyl compounds, they can be uh, reduced. They can be reduced. We just came across alpha beta unsaturated carbonyl compounds, so even they can be reduced. Internal alkynes are like suppose we have alkyne group in a different chain, internal alkynes, or it can be something like this. These internal alkynes can also be reduced using Birch reduction. Even styrenes can be reduced. Styrene, you might have heard this chemical name styrene. Recently, it was in the news. This is the styrene. Even this can be reduced. The polystyrene was in use recently. Alright, next, alkynes can also be converted to alkenes. So you can convert alkynes to alkene with the triple bond. You can convert that to the double bond alkenes. Birch reduction is method of choice for partial reduction of aromatic compounds. You know the Birch reduction will do the partial reduction. So it is uh, it is the method of choice. It is the method of choice on partial reduction in case of all aromatic compounds. So that was the application. Next is the limitation. Ordinary alkenes and olefins are not reduced under Birch reduction. The alkynes can be reduced, but the alkenes, just the alkene cannot be reduced. Or alkenes like this, conjugated alkenes can be reduced, but not like this. The one which is like this. Or olefins. This is actually olefin. This is just your I can say ethene, alkene, and if they are long chain with n number of carbon atoms, they are olefins. These cannot be reduced using the Birch reduction. That is about Birch reduction. Next, we will go for reduction by metal hydrides. There are two metal hydrides. One is sodium borohydride, another is lithium aluminum hydride. So these two are reducing agents. We are going to do the reduction using these two reducing agents. They are used separately, so we'll study them one by one. First is the sodium borohydride. So this is the structure, and this is the expanded structure of sodium borohydride. It is a metal hydride. So here is the metal. Because of this metal, it is also called as a metal hydride. So sodium borohydride. Here is the boron, right? You have hydrogen attached to it. These hydrogens are like hydride. This is hydride. Hydrogen with a negative charge is called hydride. So there are four such hydrogens are attached to the boron, and four such hydrogens are attached using covalent bond. This is covalent bond, right? Covalent bond. but this the bonding between sodium and this whole group is ionic bond. This is ionic bond. So it's a combination of a covalent bond and ionic bond. It is also called sodium tetrahydroborate. Sodium borohydrate is also called as sodium tetrahydroborate. So it is used as reducing agent. It is less reactive than the other one, the lithium aluminum hydride. We will see into that in detail. So how is it prepared? So it is prepared using sodium hydride, mixing that with the sodium hydride, mixing that with the methyl borate, and you have to heat this to 250 degrees centigrade, and you are going to get sodium borohydride. That's how you prepare that, and let's see the example here. So what is it going to do? It is going to convert aldehydes into alcohol. So sodium borohydrate, it can convert aldehyde and also ketone to the alcohol. So aldehydes are getting converted to primary alcohol, and ketones are getting converted to secondary alcohol. So we are using sodium borohydride as a reducing agent, and you are using water as a medium in acidic condition. Alright, it does not attack on other reducible groups. This is the advantage of this sodium borohydride. It it will also do the partial hydrogenation, or it will reduce partially. It it is not. Suppose you have ketonic group or the aldehyde group, and along with that, if you have the suppose you have the ester group, the acetyl group, it's not going to attack on these groups. It is not going to attack on, even suppose you have carboxylic acid group over here. It is not going to attack on it. It is not going to reduce this. Right? It is not going to reduce esters, acids, nitriles, nitro or lactone groups. Nitrile is that is nitrile, and lactone. Suppose if you have something like this, that is lactone. These are not going to get reduced, only the aldehyde. It will reduce only the aldehyde and ketone groups attached to it. Alright, let's look at the mechanism. So the sodium borohydride, it is going to convert to sodium ion and borohydride, or the hydride ion. Again, this hydride is going to give you, the borohydride is going to give you hydride ion, the one with the hydrogen. So this hydride is going to be useful over here. So because of this sodium borohydride, you are going to get hydride. So now here, like before, the carbon is going to get a partially positive charge because of the electronegative oxygen. It's going to pull the oxygen, the electrons, this double bond electrons towards it. So oxygen is partially negatively charged, and carbon is partially positively charged. So what is going to happen here? Partially positively charged, the hydride ion is going to attack on the carbon, and you are going to get this hydrogen bond. Right now, because it is partially negatively charged here uh, on the oxygen, the hydrogen of water, we are going to have water in the reaction. Okay, this hydrogen of water is going to attack on the oxygen over here. So you are going to get OH group, alcoholic group over here. So this is how you get the hydrogen attached, right, and the hydroxyl group attached over here, and that is how the ketone is going to get converted to the alcoholic group. So that is the mechanism of reaction with the sodium borohydride. So what is the application of this reaction? It's a milder reducing agent. So we can use this selectively, or we can do the selective reduction. Only aldehydes and ketones are getting reduced, that we have seen, without effect on the other reducing groups, like what we discussed earlier. Carboxyl ester and nitrile groups are going to get unchanged. So here is one example: para nitrobenzaldehyde. This is the nitro group at the para position. Para nitrobenzaldehyde using sodium borohydride is going to get converted to para nitrobenzyl alcohol. Only this is going to only aldehyde group is going to get reduced, and this is not going to get reduced like NH2. So if you want to do such selective reduction reaction, sodium borohydride is the best reducing agent. So reduction of ketonic group to alcoholic group in synthesis of tropine and alcohol. This should be cholesterol. In case of cholesterol synthesis, and tropine synthesis, so you can do the selective reduction on the ketonic group. Tropines are like atropine, right? Tropine can lead to atropine, so you come across atropine in that atropine, homatropine, all that. So even in the synthesis of cholesterol, so you can use this reducing agent. Second one, reduction of ozonides to alcohols. So here is your cyclohexene, right? On this cyclohexene, so you are going to get uh, straight chain. You are going to get straight chain carbon or the alcohol over here. So you can take cyclohexene here. Cyclohexene, you have to do the ozonization. This is the ozone, and you are going to get this is your ozonide. This ozonide, if you subject to sodium borohydride, you are going to get a straight chain alcohol with the two alcoholic groups. So that is hexane 1,6-diol. Removal of carboxyl group in phytosteroids. So you can remove the carboxyl group in phytosteroids. So this is a steroidal ring. It is not shown fully, and this is your keto group on that steroidal ring. First, you have to subject that to, and or you have to convert it to tosyl hydrogen. This is your tosyl hydrogen. Tosyl hydrogen, tosyl is like it comes from toluene. Toluene, it has got the toluene. Toluene combination of toluene and sulfonyl. So that is the tosyl group over there. So tosyl hydrogen, you have to convert that to tosyl hydrogen, and this tosyl hydrogen you are converting it to, you are removing this ketonic group using this tosyl hydrogen. So first you have to convert it to tosyl hydrogen, then you are going to remove this whole thing. You remove this whole thing using the sodium borohydride. So you can reduce glucose to sorbitol. So this is your glucose. Glucose will have that CH or the aldehyde group on the top, right? Aldehyde group on the top. But you can convert that to alcoholic group. So this is going to happen in the conversion of glucose to sorbitol. Alright, that was about sodium borohydride. Next is lithium aluminum hydride. This is also metal hydride, like I told you before. This is the structure of it. This is the expanded structure, like the sodium borohydride. Here is the lithium. Here is the aluminum. This is the covalent bond, and this is the ionic bond. These are the ionic bonds. So it is more reactive than sodium borohydride. It is a stronger reducing agent than sodium borohydride. So how do you prepare this? By gradual addition of a limited quantity of anhydrous aluminum chloride. You have to take an anhydrous aluminum chloride and you have to slowly add that to thin paste of lithium hydride. And you are going to get the lithium aluminum hydride. That's how you prepare that. So what is it going to do? It is going to convert aldehyde to primary alcohol, ketone to secondary alcohol, and it will also convert carboxylic acid to primary alcohol. So this is the difference between sodium borohydride and the lithium aluminum hydride. But here it is going one step ahead, so it is going to convert carboxylic acid to primary alcohol. So next is the application. First one is the reduction of nitriles, reduction of cyanide group to amino used in synthesis of strychnine. So here's your nitrile group or the cyanide group. So you are going to reduce that to amino group. You are going to reduce that to amino group using lithium aluminum hydride, and this is used in the synthesis of strychnine. Strychnine is the alkali. It's an alkali. Alright, next estimation of active hydrogen can be done using the lithium aluminum hydride. So lithium aluminum hydride, it evolves molecular hydrogen. It's going to evolve the hydrogen because it evolves those hydrogens, active compound containing active hydrogen. There is a compound containing active hydrogen. So it is going to, because it is going to evolve hydrogen, it is used in the determination of active hydrogen. You can determine, it is used in the analytical methods to determine the active hydrogen in the molecules. Next, you can do the reduction of sulfonyl chloride. You can reduce the sulfonyl group here, but sodium borohydride is not going to do that, but it can reduce sulfonyl chloride. It can reduce sulfoxide group. It can reduce sulfone group, right? It can reduce sulfonyl group. It can be used for reducing pyridine and oxide. This is the oxide, pyridine and oxide. This is an oxide. So you can reduce that. So what are you going to get? So you are going to remove oxygen over here. So with that oxygen as well as this chloride group, so you are going to replace that with the hydrogen. So from sulfonyl chloride, you are going to get the mercaptan or a thiol group. So thioxide you can convert to thioether. This is like the sulfur in the in between R and R. It is going to be like that thioether. So you, instead of you are going to remove oxygen here, and here you are going to remove the oxygen again, sulfone. You're just going to retain the sulfur over there. Then you are going to remove oxygen here again, right? And you are going to remove oxygen from here. So you can convert all these products, sulfonic chloride, sulfoxide, sulfones, and pyridine N oxide using the lithium aluminum. This completes about these three topics, two reduction reactions, Clemmensen reduction reaction and Birch reduction reaction, and we also studied two reducing agents. One is sodium borohydride and another one is lithium aluminum hydride. And thank you very much, and let me know if you have any questions.